likelihood was invented a long time ago by the statistics, and we are not going to go through any theories and so on. But the actual people who apply those methods to phylogenetic analysis is Geoffrey Sandstein. He's the one who really do that. And basically, you can apply some of the chi-square test and so on to see which one is the better one and calculate the likelihood. And we'll work on that a little bit later on. So for the maximum likelihood, and the likelihood L is the probability of the data given the hypothesis, and the hypothesis is the tree. So basically, we want to evaluate the different tree and provide and to calculate the likelihood and using this formula right here. And how to calculate this one, and that's the beauty of it, of the maximum likelihood. But before we do that, we need to have some practice about some of the concept over here. So here is just an example. We want to solve the problem for the actual population proportion for the red and the blue fish from a pond. And we have no idea about the population size for, in advance. So we just sample 100 fish from a pond, and we got 10 redfish and 90 bluefish. So the best estimate for the proportion of the fish in the pond will be 0.1. And this is a very straightforward concept, right? And actually, if we give you the function of this proportion from 0 to 0.5 and give you this kind of a curve, then you will see 0.1 has the highest likelihood value, and for the others, and 0.2 is the less likely, but it's still possible. And over here, it's probably very less likely right here. So if this function is true, then we'll see 0.1 is probably not the only answer, it's the best answer, but there's a very similar value right here. So it's kind of, we are taking the value right here as just a best estimate for the proportion we just got. So it's a relative concept, and we can do that for this probability concept in this nucleotide substitution as well. And we can calculate the distance by using the probability concept. So again, the distance method, we can use several different methods to calculate it, and we already do a very similar exercise before, and we can calculate the actual differences based on the probability of the change. And so we can skip this one. So for example, we observe a certain site of the nucleotide is ACGOT, and for example, in this case, the probability from T to C of T can be calculated according to this formula. And this formula looks a little bit complicated, but it's not. It's basically over a period of time, T, the probability of a certain substitution will be the summary of this one. And the summary is based on the IJ is from a certain nucleotide to another nucleotide. And you can calculate that based on your observation of the sequences. So if you have a sequences, for example, ancestral sequences is poly-T, then how you can calculate the ADN probability of substitution. And the substitution will based on your proportion of the observed data, and then it will converge over the time. And doesn't matter it's started with poly-T or poly-A or poly something else, and it will converge to the proportion for the observation of the nucleotide percentage. Like in this case, this equal percentage for ACG and T. So anyway, as long as the T is known, then the calculation can be done in this case in equilibrium. So the probability and likelihood have some different properties, and we already mentioned a little bit about it. And the probability is a function of data with the parameter given. So we just give a certain substitution model, for example, then you can have a function of that. And for the likelihood, and we'll basically observe the data and obtain a function of the parameters itself, and to see if it has a higher or lower likelihood in this case. So the probability has sums to 1, so it's always from 0 to 1 in this case, and this is a likelihood will be a relative number, and so we need to use like the chi-square to decide if it's better than the other one. So let's go back to the actual tree problem here. And the likelihood calculation on the tree is going through this process. On the top is the data matrix we got, and sequence 1, 2, 3, 4, and from 1 to n characters. So we just calculate one character at a time. For example, we use the character number I, pi, as an example. And we eventually will calculate the likelihood for all the characters, and it will be expressed by this formula right here. So how do we do that? Basically, in this case, we move back to the 4-branch problem. The character I, we put the 4 different taxa at the end, 1, 2, 3, and 4. Then it's GGCT in this case, right here. So we want to estimate what is the likelihood value, I mean the history or the probability for this thing to happen. And we notice that there are 2 internal nodes right here, J and K. So basically these 3 are the same, so we'll use that tree to explain as well. So it means that in the ancestral node, that's J, and right here we have a K. At the end, we'll get G, G, C, and T for the node. So for the J and K, there are 16 possible combinations, right? So it's TT, TC, TA, GG, until AA, and so on. So there are 16 probabilities we need to calculate. And we can calculate every single probabilities according to the probability calculation, which is C from previous slides. So for example, there's a T to G probability change and T to C probability change. And we'll calculate every branch and summarize everything into one value. That's the probability for this particular hypothesis for the ancestral state reconstruction. So we have to add up all of the 16 possibilities for a single character. That's one character. And we have to calculate all the characters. At the end, we'll have a very complicated formula to summarize every possibilities. And that's the simple case for 4 taxa. And you will imagine that once you have more taxa, there will be a lot of trees you need to evaluate. And that's why maximum likelihood takes a really long time to calculate that. Because before the actual likelihood ML method to analyze, we need to decide which is probably the best substitution model as well. So we need to do something in advance and to see how do you know this is the best model. So sometimes the best way will be calculate the different models like the Jus-Cantor, Kimura parameter, or GTR, or HKY, and to calculate the different models and to calculate everything again to compare which one is the better one. But this is really tedious work to do so. So sometimes the way we choose the best substitution model is to have a tree first, and based on a particular tree, and then we can speculate the different substitution model. But how do we get a tree first? And that's a big problem. So for the programs like a model test for choosing the best model, we are actually put up some hypothetical trees which could be derived from neighbor joining, which is faster, or something else. And then we can just, based on that, to calculate which one is better. So we'll see this is actually a loop of the calculation. So we are choosing the best model, but we are obtaining the trees is we have no idea if that's true. But we use this to estimate the best model and use the model to find the best tree. So it's kind of a very strange situation in a sense. So this is just give you some idea about, well, okay, this is a kind of very difficult calculations we can get. And this is, again, the same idea for the 16 combination for the 4 taxa problem. And we have AA in the middle, TLGG at the end of the formula right here. This is character number 5 right here. And the overall likelihood will be L1 times L2 until Ln. And for calculation purpose, we'll have a log of this value, and we'll compare the log for the chi-square test to see if one over is better than the other. So this is the same thing. The criteria here is to have an ancestral reconstruction, and just like the tree, the possible trees for adding more taxa, there will be more internal nodes for this ancestral reconstruction, and therefore it's very difficult. In the previous case, we only need to calculate 16 probabilities, right? But if the internode has more, then we'll have more things to calculate. That's very difficult, actually. And the likelihood, however, is still better than the maximum possibility, and methods incorporate the substitution model in the calculation anyway. So this is something different. And how is the ancestral reconstruction is important? And this is an example. It's a paper published in Science, actually. It's talking about history of the fluorescence gene. So they will have certain genes and put phylogenies from the genes. And we can actually see the evolution of the genes from here to here, and actually the different color of the fluorescence of the gene product, I mean the expression, then it can give you some idea about the ancestral state for a certain gene function. So for example, right here, and we'll have a red fluorescence as an end product. And so we'll have the spectrum based on this ancestral state. And also here we can have ancestral reconstruction for the spectrum as well. So we can just keep moving back and back and eventually get something that's hypothetical ancestral construction for the ancestor states. So this is has some applications on how do we reconstruct the origin, I mean the ancestral form of something. So this is something we can do anyway. So there are some assumptions for the maximum likelihood, and this is the same thing for the others. And it assumes the evolution among the different sites is independent, and also the different lineage is independent. And this is quite easy to violate anyway. But for each site, we already demonstrate this is the idea we got. The likelihood is a probability of the taxa given a particular tree. And that's one single tree. So again, we know how to calculate that. For a particular tree, it's already very complicated. And we have to calculate a lot of trees, just like the maximum possibility case. Because we are moving from one spot to the others, and just to evaluate the likelihood value between here and also here. So you will face the very same thing as maximum possibility, as you will go trap. It's possible to be trapped in a tree island among the tree landscape. So again, to avoid this problem, the best way is to have a random starting point, as many as possible, to starting from here or from there. So the more, the merrier. But it's almost impossible to do so, as if you have ever run the maximum likelihood yourself, then you will know one run of the maximum likelihood will take hours or days to finish it if you don't do any approximation of the analysis. But right now there are some programs they can do that. But again, if we want to have a random starting point to do that, then it will take double or triple times or 100 times to finish the analysis. That's not realistic. So at the end, for the past decades, for the people who wants to do the maximum likelihood, if you are dealing with over 20 genes or 20 taxa, then it almost is not recommended to use maximum likelihood. But a couple of years ago, some people developed some new method to approximate the process and largely reduce the calculation time for maximum likelihood. That's the program GET, and we're probably not going to practice that. But right now you can deal with 100 genes using this program with reasonable time, which means a few days or only a couple days. And if we are using a computer cluster, then it's faster. If we are using this computer, it takes much longer. And we have one example is the largest data sets for a long time ago, 20 years ago. There's 500 genes, and they try to use the maximum likelihood method to get the best estimate for the best tree. So the program 20 years ago, it runs on 40 megahertz machine. So it's quite slow compared to nowadays computer. And it takes 6 months and still not finished. And they have to stop because they want to publish the data. So it really takes a really long time, as you can imagine. So you have to be very careful on maximum likelihood anyway. So for some problem, it's possible to do that because it seems to be a good method to estimate. So if you are only interested in the problems of human, gorilla, chimpanzee, there's only 4 taxa, right? So it's very easy to calculate it. You can add up a lot of sequences and try to get the best estimates. But for the others, it's not that suitable. So that's probably the reason why Bayesian inferences is getting popular for the past 10 years anyway. So we already mentioned this. The likelihood, the probabilities totally depend on the model selections. Usually the more complex model you select, it will give you a higher likelihood value to say that is better. But sometimes it's not necessarily true. And we'll give you some example for the test, for the likelihood ratio test. If you are not familiar with it, you have to look at it here. And we are going to calculate the value here, the log L1 minus log L0. And L0 is the null hypothesis, and the L1 is from the alternative hypothesis. In this case, it will be tree 1 and tree 2. And we want to calculate the tree. In one case, we want to evaluate the tree is better than the others. And sometimes you can calculate a lot of things. This is basically called hypothesis testing. And so we introduced here a little bit earlier. And so we can calculate this and use this number to find the chi-square distribution. The degree of freedom is only 1 in this case. Well, if there's tree number 1 and number 2, then there's no degree of freedom of tree in this case. But if we are comparing about the different models of the substitution, then we can calculate the degree of freedom accordingly, and then we just find out if it's significantly better than the others. So this is an example for likelihood ratio test. What we are going to test is to see if one substitution model is better than the other one. So here is a sequence from Choroplast. It's MET-K sequence. It contains a coding region and also the franking region from the intron of tRNA. So we are going to separate the different regions and to see if a particular substitution model is better than the other one. So we'll compare the null hypothesis L0 to L1. So here is the data table from the full-length coding and non-coding. If we consider the full-length only, and what we are going to test here, juice canter over HKY85 or choose Cantor versus GTR or HKY85 versus GTR, the three different models, and we can calculate if it's better than the other one. The gamma one will explain this a little bit later. Based on this one, we can calculate according to a different degree of freedom, and eventually we'll get the number, and we put a star, and that means that it's significant under the chi-square table. So for the full-length coding and non-coding, the alternative hypothesis is always better than the null hypothesis based on the result, which means that more complicated model is always better than a simpler model. And eventually we'll get GTR plus gamma is the best model for estimation for everything. And this is just an example for choosing the model over the other. So we can just do the simple test by hand. And also some program can do that as well.